but it does take a certain amount of creativity, which now is not going to be required because we have formalized this. So an arithmetic progression is based on addition with the philosophy that every subsequent term is separated by a same difference. So if the first term is a, then the next term will be a plus d, then the next term will be a plus 2d, and so on. So for any progression for which you have terms defined, it should be defined in terms of the position within that sequence. So I should have a formula for the term expression in terms of the position which we are going to now refer as n. So nth term would mean, for example, if I say third term, it would mean 1, 2, 3. Third term from the starting. The term expression for arithmetic progression is Tn is equal to the first term plus n minus 1 times d, where d is the difference, d is the common difference, which is separating each term from the neighboring terms. So the proof of this is very clear. I don't want to get into that, as part of revision module. You have your first term and then you continue to move n minus 1 into d, n minus 1 differences to get to your nth term. The summation expression for an arithmetic progression would also be described in a similar way with a, n, and d. These are the three variables that we are going to play upon. So Sn is going to be n by 2 times 2a plus n minus 1 into d. This formula can be rearranged into saying that Sn is equal to n by 2 times sum of the first term and the last term. And if you send this 2 inside, what you are really saying is that an arithmetic progression, the sum of it can be represented as the number of terms that are there into the average of the first and last term. F plus L by 2 is the average of first and last term. A phenomena which can help you reduce a lot of calculations. All right. This can also, if you do want to, which is honestly a bit of an overkill for CAT, you can also represent this as n times third term from left plus third term from right divided by 2. The reasoning being, and this you can replace with the same, you can say fourth term, fifth term, sixth term, doesn't matter. What we are really saying is that the sum of the first and last term, or rather sum of the terms equidistant from either sides, is going to be the same, and it is going to be equal to first and last term sum. This one honestly is not that much required. Your main formula is going to be this one, and this one is a good trick to reduce your calculations, because if you do get your first and last term, you do look at a situation where a and d is something you might not even have to solve for. All right. uh, Okay, let's move ahead. If you do have to assume the terms, for example, they say that there are three terms in AP or four terms in AP, you will assume it as A plus D, and A minus D. If they say three terms, if they say five terms, you will do A plus 2D and A minus 2D. These would be your five terms. So if they give you odd number of terms in an AP, it's a good idea to have your central term as A. So while in a general sense, A represents the first term, but you can always reshape the situation to your advantage. And the advantage here is if I add these five terms, I directly get 5A. So I am getting the value of the central term through this representation. Furthermore, the products are going to be very simplified. If you multiply these three terms, you will get A into A square minus D square, which is a much more elegant result as compared to A into A plus D into A plus 2D. So it's up to you how you decide, how you want to assume the terms. Again, this is a situation which they will specifically call for, that there are seven terms in an AP. So then this should strike you that maybe taking those as A minus 3D to A plus 3D is the better way to go for. However, if there are even terms, even number of terms, you will have to do it like A plus D, A plus 2D, a minus d and a minus sorry a plus 3d and a minus 3d. So in this situation your common difference will turn out to be 2d, and this is where the room for calculation mistakes increases, because in your mind it would be hardwired that a and d are first term and common difference respectively, and in this situation you are purposefully writing the common difference as 2d. So the likelihood of you finding the value of d and then marking it as the answer for common difference is very high. So I would say, if you do come across a situation where there are even number of terms in the AP, might as well let it be. It's a good practice, it helps you. I agree with that. It will help you find the value of a very fast. If you add all of this, you will get 4a. However, the likelihood of making the calculation mistake increases. With this, let's move towards the scenarios that you can come across in arithmetic progression. In terms of weightage within this topic area, I would say generic sequences, which we will discuss toward the latter half, is more than half of the topic weightage. Then you have AP, and then you will have GP, which really only gets asked in a one particular scenario, which is infinite GP. All right. So let's discuss APs first. So AP is more important than GP. So let's build upon AP. You can have standard questions in arithmetic progression where they give you certain data points and they ask you to find some variable or some different thing which you can express in terms of the known variables. So the thing to understand here is that for you to define an arithmetic progression, for CAT to define an arithmetic progression, they have to define what is the first term, what is the common difference, and n, the number of terms, is generally not used as a variable. It is generally used as something which is given. So these two things are technically all you require to define an arithmetic progression. And once you have that arithmetic progression defined for you, it does not matter what they ask us. So because there are two variables, they should ideally give me two or more equations or certain constraints which will help me narrow down on the value for a and d. So your target always, when you get across a standard question in arithmetic progression, and when I say standard, I mean like a word problem, that this is this is that sort of situation, then maybe you should focus all your energies on finding a and d. And this is only for standard situation. Any other specific situation we are going to be tackling very soon. And once you have a and d, you have your arithmetic progression defined, and then it does not matter what they ask. You can reshape the AP into whatever you want. uh, we will see an example of this, what I mean. So what is more important in this particular context of a standard arithmetic progression is to understand how can they give me the information, because the end goal is clear, to find a and d, or in some context n. Now second situation is intermediate zero sum, which is a very nice sort of result. So let me say that there is a statement like this: sum till term number m is equal to sum till term number n. And let's put some values here. Let's say I give you an AP, the sum of first three terms is actually equal to sum of the first 10 terms. Now would that mean that sum of the first three terms plus term 4 plus term 5 plus term 6 plus term 7 plus term 8 plus term 9 plus term 10 is equal to sum of first 10 terms? This is what you will write, because S3 includes what? T1 plus T2 plus T3. Now, if this is equal to this, can I say this part, sum of terms from term number 4 to 10 is going to be 0? This is going to be equal to 0. And when this is 0, if this sum is equal to 0, is this not in itself an AP? This is a section we will we have categorized it separately, but any subset of an AP would also be an AP if you take continuous terms. So would that not mean that the average or the sum of these you know uh, 7 terms would actually be T7 into 7? If you look at it from that perspective, a plus d, a plus 2d, a plus 3d, and the a minus d terms on the other side, and if you add, you will get 7 times term 7. This is equal to 0, which means term number 7 will have to be 0. And this is a very nice result because it tells you that till term 7 you are going to have a particular sign, maybe positive, maybe negative. Term 7 becomes 0, and after that your terms are going to be negative if previously the terms were positive. So this would either be a decreasing AP or an increasing AP. Clear so far, everyone? Okay. However, if the terms were even, if let's say I had given you S3 is equal to S7, so then you would have said S3 plus T4 plus T5 plus T6 plus T7 is equal to S7, and then this is equal to this. So you will get this sum is equal to 0. Now, can you say that there would be a term which will have a value of 0? No, you cannot say that. What you can say is T5 mod will be equal to T6 mod, but with opposite sign. So these two will add up to 0, these two will add up to 0, and so on. That is the result you are getting for this particular instance. A result which was true for odd also. For example, whatever value T6 will have, it will be same as T8 but of opposite sign. Why? Because T8 is what? 0 plus D, that is D. T6 is what? 0 minus D, that is minus D. So same value but opposite sign. So their sums would be 0, which is again something you can understand from the fact that we previously mentioned that sum of terms equidistant from the center or from the ends would be same, and same as the central term. So this is a fun situation. The only relevance of this is to arrive at this 0 term. Otherwise, it's a standard arithmetic progression question only. You can hypothetically find the expression for S3, equate it to expression of S10, and that would also give you the same result. All right, let's move ahead. Now, the most common sort of situation within arithmetic progression is finding the common terms. If I give you one AP, let's say AP1, and if I give you another AP, AP2, and when I say I give it to you, what do I have to give you? The values of first term and common difference for both of these. Now, what can be asked is what are the number of terms or what are the terms that are present in both of these? A situation we just saw yesterday when we were finding the time period of meeting uh, when you're moving along a circle. Time period of meeting at the starting point, a sequence we a situation we have dealt already. So how do we do that is you first find the first term which is going to be common to both of these. uh, Generally hit and trial would actually be the fastest method. Once you arrive at the first term, the next term which will be common to both will have this first term plus the LCM of the differences that both of these APs individually have. So what we are really saying is that the common terms would also form a separate AP with the first term as this term that we found by hit and trial, and common difference as LCM of the differences of these two APs. Now, once you have this new AP of the common terms, you can forget these two, unless there is some constraint, which we will see again. And then whatever they ask you for, maybe they ask you for the smallest three-digit number, which is common to both of these. So what they are really asking is in this new AP, which is the first three-digit number? They can ask you for sum of common terms. Doesn't matter. Once I have the AP, I don't really care what they ask me. I'll just give it to them. Now, geometric progression, we don't really even have to, waste time on this. This is a product result. Each term gets multiplied. Each term takes the previous term and multiplies with it something we call as the common ratio. So the division of subsequent terms gives you the same number, which is R, which is called as the common ratio. So your term expression will be Tn is equal to A times R raised to power n minus 1. So in order to define an AP, you need two things: the common, the first term, which is A, and the common ratio. The sum expression for a GP is Sn is equal to A times R to the power n minus 1 divided by R minus 1. Okay. Again, assuming terms in a GP is something which rarely gets asked. I mean, products. But if they do, so then you will take as what? AR, A by R. Then you will take it as this format. I don't really think this is something that will happen. The AP thing itself is something that rarely happens. So might as well let this be. So the only two things of note here are TN and SN. The reason why SN is important is not the actual value of this, but this is important for two reasons. Reason number one is if you put common ratio as something less than 1 and then you put n as infinity, you will get this r raised to power n become insignificant as compared to 1, which will give you s infinity is equal to a by 1 minus r. So infinite sum is defined for a GP. There is no sense of having infinite sum for an AP. All right. The second thing which is important is the proof that we use to get to this, value of Sn. I will not show you that again here. I will directly show it to you in an application format. However, what it required was you wrote the sum expression and then you multiplied the sum expression with r. You got something, and then you took the difference, which enabled you to get something on RHS, which is very easily calculated. So with that, in geometry, in geometric progression, you can again come across two types of situations only. Apart from infinite GP, one would be a standard situation. Again, it is very clear. They will give you some data points similar to the question that we saw for AP, and then they will ask you for something. So in this situation, your agenda should be to find the values of A and R, sometimes N if it goes to that extent. Section of a GP. A GP is, if you take a smaller section of a GP, it will still be a GP, because the fact that something is a AP or GP does not depend upon the overall sequence. It only depends upon the next and previous sequence, next and previous term. And as long as you are maintaining that, it doesn't matter which section you pick. So a section of a GP will also be a GP. Something which is used a lot in infinite GPs. All right, so again, I'll show that to you an example. Infinite GP is one of the only available areas where infinite sum can be finite, which means whenever we come across a situation where they're asking us for infinite sum till infinite terms, we should immediately think of infinite GP as something to try, because it's the most common go-to case. And secondly, even within an infinite GP, section rule will apply. And what I mean by that is, let's say there is your infinite GP 1, 1 by 2, 1 by 4, 1 by 8. Now let's say I picked this section. This section would still be a GP and would still be an infinite GP. That is what I mean by section rule applies for an infinite GP as well. And which is something they often do. They will give you the sum for this GP and they will not give you what this first term is, and then they will build upon that. So special summations, these are formulas that at this point we are not going to talk about the proofs. We are going to memorize these immediately. I have plenty of times described the proofs, so that is now not on me. Sum of first and natural numbers, you should know these. N into n plus 1 by 2. Sum of first n squares, it's going to be n into n plus 1, so far similar as the previous one, into 2n plus 1 divided by 6, divided by 2 into 3. All right. Sum of first 10 cubes is the square of this. N into n plus 1 by 2 whole square. Okay. Sum of first n odd numbers. N square. Sum of first n even numbers. N into n plus 1. These two are probably not as important. This one is highly important. You might end up using it, in other topic areas as well, not just sequences and series. And this one is these two are wild cards. They might get used, and they have gotten used in CAT itself. And those who didn't know the formula, would not have known, how to solve this. Major chunk of this particular topic area, the only area where you might come across issues, unless it's a 2023 paper, generic sequence. They have not told you what the sequence is. They have not said this is an AP or a GP. We don't know what it is. They just give you a sequence and then they ask you to, boss, tell me what's the sum, what's the term number, etc., etc. Within this, we are going to follow this framework. First of all, we will see, are they asking us for infinite sum? If they are asking us for infinite sum, probably it's a question of infinite geometric progression. Or otherwise, there would be terms that are getting cancelled. There is no other way for you to calculate sum of infinite terms unless either you know the formula or you don't really need to calculate it, which is when terms start to cancel. So terms can cancel in two ways. They can either cancel as differences. So the question becomes, how do you break each term into differences that starts to cancel, or as products? So maybe they don't give you an addition sequence, they give you a product sequence. And then it's for you to realize that yes, maybe the numerator of the first term that I have is cancelling the denominator of the third term. All right. This is easily noticeable. This is something you don't really even have to keep in your mind. Infinite, logically, yes. Either I know the formula or I have to make it into something that I can calculate. Fractional sum is also something which is immediately noticed when they are asking you to add fractions. All right. Because they will have to write the fractions, your mind should immediately go here that this is fractional sum. Now, when you are dealing with fractional sums, again, these categories are not mutually exclusive. If you are working on that, you know, uh, view, that is not true. You can have fractional sum and infinite together. Infinite fractional sum you can have, which is one of the ways where your differences manifest. However, if your denominators are surds, something like a plus root b or root a plus root b, what is it that you will do? If your denominator is of this format, what will we do? We will rationalize. We will get rid of the denominator. See, adding fractions is going to be difficult anyways. You will never be required in an CAT exam to actually take LCM of 10 different fractions and then add those. So there is going to be a smarter way. And if there are surds in the denominator, the smarter way is this, that you rationalize the denominator. Most probably the denominator once rationalized will turn out to be something which is same for all the fractions, in which situation the fraction part is removed. The second situation in which we will shortly see is numerator as denominators factors difference, in which case it breaks as your differences and terms start to cancel. Now you can have an AGP situation, AGP or AGP ish, where what you really have to do is calculate SN minus RSN. Doing this turns this into an expression which is one of the aboves, for which I know how to calculate the sum. And once I do that, I am okay. The trick is to observe that there is a common ratio going on, and the common ratio generally in AGP sort of situations where you are required to calculate this SN minus RSN, generally the common ratio is in denominator. It's a denominator thing. So again, your mind should strike that this is getting out of hand. One other thing about AGP sequences, it's absurd. It looks like something that, boss, I can't do it at all. What have they asked me? It looks very difficult to solve. And this could actually be a hint that, boss, this is an AGP situation. I'll show you with a CAT example only. Then you will have generic situation when all else fails. Then what we can do is find first few terms and identify a pattern. Now obviously this is not something we will do for fractional sums. Finding first few terms is going to be complicated there. This is generally used where they give you that tn is in terms of tn minus 1. And now I would like to make a callback to our generic functions lecture, right? There also we had this situation. F of n is equal to f of n minus 1 plus something. And what was one of the key ways to solve there was to find some few terms and maybe the pattern will click us. Other few things that can happen is maybe once you start writing the terms, you realize that the terms are repeating after a certain point. So there's a repeating block, in which case they would have asked you for something absurdly high. Find the value of A2022. and they give you something like this: differences of the sum. Now, if they have given me an Sn expression, I can get Tn as Sn minus Sn minus 1, because Sn minus 1 will include 1 to Tn minus 1, and Sn will include 1 to Tn. So when you subtract these, only Tn will remain. And finally, you can have a situation where you have AP into AP. A thing that you will have to first notice that, boss, this is an AP into AP, and then you will quickly realize I can find the Tn value, and the Tn value will be made up of n and n squares, for which I know the sum. How? Like this. All right. So infinite series we have covered. You can either have infinite GP, or you will have something which cancels out. There is no other way to calculate this. Fractional sum, again, if there are surds, you will rationalize. And if it's not surds, then you would probably have a situation like this: 1 into 2 into 4 plus 1 by 4 into 6 plus 1 by 6 into 8, and so on. So the clever thing to do here is to realize that the differences of the denominators, the factors, are constant. So if I write this as 2, this is 2, this is 2, and how will I do that? By multiplying it whole with 1 by 2. I can write this as what? This 2 I can write as 4 minus 2 divided by 2 into 4, which becomes 1 by 2 minus 1 by 4. The next term will become 1 by 4 minus 1 by 6. The next term will become 1 by 6 minus 1 by 8. These will start to cancel, and you will be left with 1 by 2 only. Now, generic sequence in the AGP format. These will, look difficult. These will look difficult. So one of the markers for doing this is that actually, boss, these are going to look very difficult. All right. The second thing is you should have something going on, and listen to this carefully. Each term should be made up of two parts. One part is part of a GP. The other part should either be an AP or something which is part of a additive sequence as compared to the previous term. So it does not have to be that the differences are same. It's just that something should get added here, and then something related should get added here to get to the next term. Okay, finally, to the generic sequences part. This is the situation where from the get go you don't have a lot of information. You don't have something which is immediately clicking, like infinite sums or fractions or rationalization, etc. This is most probably in a word problem format, in which situation finding the first few terms is actually going to be really, really helpful. And Chetali, you had asked, right, how to figure out that we should maybe find the first few terms. It would actually be almost explicitly written in the question itself, and I'll show you how. Some specific examples here can be AP into AP, repetiting blocks, or differences of summation.